To detect the most violent cosmic events in the universe, like colliding black holes, astronomers don't look through giant telescope lenses or listen to the sky with massive radio antennas. Instead, they measure the physical stretching and squeezing of space-time itself using a massive machine called the Laser Interferometer Gravitational-Wave Observatory, or LIGO. This machine is composed of two massive facilities shaped like giant Ls. These structures house ultra-vacuum pipes that extend 4 kilometers outward at a perfect 90-degree angle. The measurement process begins when a stable, high-power infrared laser hits a beam splitter positioned at the corner of the L. The splitter divides the light perfectly in half, sending beams down the X and Y arms. Inside Fabry-Perot cavities, mirrors catch the light, reflecting it back and forth 300 times before it recombines at the center. By trapping the light in this loop, scientists artificially extend the length of the arms from 4 kilometers to an effective 1,200 kilometers, creating a scale large enough to track almost impossibly small changes in distance. After making those hundreds of trips, the two laser beams finally return from their respective arms and meet back at the central beam splitter. This is where LIGO employs its core trick, destructive interference. The mirrors are positioned perfectly so that when the beams recombine, their light waves are entirely out of phase. Because the X arm's peak perfectly fills the Y arm's trough, the two annihilate each other. As a result of this perfect cancellation, no light ever makes it past the beam splitter to reach the final photodetector. Under normal conditions, that detector sits in absolute complete darkness, trapped in an artificial void of its own making. To detect the most colossal, explosive cosmic collisions in the universe, scientists had to build a machine designed to look into perfect nothingness. That baseline of darkness holds until a gravitational wave from 1 billion light-years away washes over the Earth. As the wave passes through, it temporarily stretches the fabric of space in one direction while squeezing it in the perpendicular direction. When the wave hits LIGO, it physically stretches the 4-kilometer X-arm while simultaneously squeezing the Y-arm, alternating back and forth as the ripple rolls past. Because the physical space has warped, the light traveling down the stretched arm suddenly has to travel a fraction of a millimeter further than the light in the squeezed arm. When these two beams meet back at the splitter, their timing is now ruined. The light waves are no longer perfectly out of phase. The destructive interference is broken. Because the waves no longer cancel each other out, light begins to escape. Flashes of light finally hit the photodetector, flickering with the exact frequency of the gravitational wave. This fragile equilibrium of darkness serves as a cosmic tripwire, a silent baseline waiting for space-time itself to ripple through the facility. Measuring a gravitational wave involves tracking a distance of roughly 10 to the negative 18th meters. That distance is approximately 1/10,000th the width of a single proton. Capturing a movement that small requires isolating the machine from every earthly vibration, from trucks driving on distant highways to ocean waves crashing on the coast. To solve this, the mirrors are suspended in active damping systems. These multi-stage pendulums sense environmental noise in real time and push back to keep the mirrors perfectly still. Even with the mirrors isolated, scientists hit a final hurdle at the microscopic level: shot noise. This happens because photons don't arrive in a perfectly smooth stream, creating a quantum flicker that can mask the signal. To clear this, LIGO uses a technique called quantum squeezing. It relies on the Heisenberg uncertainty principle, which states that certain pairs of properties, like a photon's arrival time and its energy, can't both be known with perfect precision. By squeezing the uncertainty out of the arrival time and pushing it into the energy, researchers can smooth out the photon stream and clarify the signal. We can only trust that final flicker of light because of these extreme layers of mechanical and quantum filtration. By engineering a system that isolates light and cancels it into absolute darkness, humanity built a machine sensitive enough to watch the unseen fabric of the universe ripple.